What if the fastest thing in the universe has never actually moved the way you've imagined? Every science class, every documentary, every animation you've ever seen has shown light racing across space like a tiny glowing bullet. It leaves the sun, travels for 8 minutes, reaches Earth, and illuminates your face. It seems so obvious that we rarely question it. But what if that picture is fundamentally wrong? What if light doesn't experience its own journey at all? What if, from the perspective of a photon, a particle of light, the moment it is born and the moment it disappears are somehow the very same instant? It sounds impossible, yet this strange idea sits at the heart of modern physics, and few people have explained its consequences more brilliantly than theoretical physicist Leonard Susskind. To understand why light doesn't move the way you think, we have to abandon the comfortable world of everyday intuition and step into a universe where time stretches, space bends, and reality behaves in ways that seem almost designed to challenge common sense. Human beings evolved to understand objects that move slowly. We throw a ball, watch a bird fly, or see a car drive down a highway. Our brains are built from millions of years of experience with speeds that are tiny compared with the ultimate speed limit of nature. Because of that, we instinctively imagine that everything moves through space in roughly the same way. Faster objects simply cover more distance in less time. It feels natural. It feels obvious. But nature has never promised to match human intuition. For centuries, scientists believed light behaved much like any other moving object. Isaac Newton imagined light as streams of tiny particles traveling through empty space. Others argued that light behaved like a wave, spreading through an invisible substance that supposedly filled the universe. That mysterious medium was called the luminiferous ether. According to 19th century physics, light needed this invisible ocean just as sound needs air. It was an elegant idea. It was also wrong. In 1887, two American physicists, Albert Michelson and Edward Morley, performed one of the most famous experiments in scientific history. If Earth were moving through this invisible ether, then light should appear to travel at slightly different speeds depending on the direction it was measured. Imagine running on a moving train. Running toward the front feels different than running toward the back because the train itself is moving. Scientists expected light to behave similarly. Instead, something astonishing happened. No matter how carefully they measured, light refused to cooperate. Its speed remained exactly the same, again and again and again. The experiment was repeated with increasing precision over the following decades, yet the answer never changed. Light behaved as though the ether simply didn't exist. The scientific community faced an uncomfortable crisis. If light wasn't traveling through something, then what exactly was it doing? For nearly 20 years, physicists struggled with this mystery until, in 1905, a young patent clerk named Albert Einstein proposed an idea so radical that it completely reshaped our understanding of reality. Einstein made a bold assumption. Suppose the speed of light is not merely constant because of some hidden mechanism. Suppose the speed of light is one of the fundamental rules of the universe itself, not approximately constant, not usually constant, always constant, no matter who measures it, no matter how fast they're moving. Imagine standing beside a railroad track while a train rushes past at incredible speed. A passenger on the train switches on a flashlight pointed toward the front. Common sense says you should measure the light moving faster because it inherits the train's motion. That's exactly what happens when someone throws a baseball from a moving truck. The ball's speed combines with the truck's speed. Light refuses to play by those rules. Whether you're standing still, driving a car, orbiting Earth aboard the International Space Station, or racing through the galaxy, you always measure light traveling at exactly the same speed in a vacuum, about 299,792 kilometers per second. Not because your instruments are broken, because reality itself adjusts. This is where the story becomes almost unbelievable. If everyone must agree on light speed, then something else has to give. That something is space and time. Instead of light changing its speed, time changes its pace. Lengths change their size, distances shrink, clocks tick differently. Reality bends itself to preserve one universal constant. This wasn't philosophy, it was mathematics. And eventually, experiment after experiment confirmed Einstein was right. Leonard Susskind often emphasizes that relativity is not about appearances or optical illusions. These effects are physically real. Moving clocks genuinely run differently. Distances genuinely contract. Modern technologies like GPS satellites must account for these relativistic effects every single day. Without Einstein's corrections, your phone's location would drift by kilometers within hours. The universe quietly obeys these strange rules all around us. We simply don't notice because our everyday speeds are far too slow. Imagine two identical twins. One stays on Earth. The other boards a spacecraft capable of traveling close to light speed. After several years, the traveler returns. To everyone's surprise, the astronaut is younger than the sibling left behind. This is not science fiction. It is a direct consequence of special relativity. Time itself has flowed differently for each person. The faster you move through space, the slower you move through time. At first glance, this sounds impossible. Time feels universal. Every heartbeat, every sunrise, every birthday. Surely everyone experiences the same ticking clock. Yet nature disagrees. Time is personal. Each observer carries their own clock through space-time. This idea fascinated Leonard Susskind because it reveals something profound about the structure of the universe. Space and time are not separate ingredients. They form a single fabric called space-time. Every object moves through this four-dimensional arena, but the way that motion is divided between space and time depends on the object's speed. Imagine your motion through space-time as a fixed budget. If you spend more of that motion moving through space, less remains for moving through time. Slow down through space and time races forward. Speed up toward light and time begins to slow. Approach light speed closely enough and the flow of time nearly freezes. This leads to one of the most astonishing ideas in all of physics. What about light itself? If moving clocks slow down more and more as they approach light speed, what happens at light speed? The mathematics points toward an extraordinary limit. From our perspective, light takes over 8 minutes to travel from the sun to Earth. It takes over 4 years to reach the nearest star beyond our solar system. It can spend billions of years crossing the observable universe before finally entering a telescope. Yet according to the equations of relativity, a photon does not experience the passage of time in the way ordinary objects do. Physicists are careful here. Strictly speaking, there is no valid rest frame for a photon in Einstein's theory, so we cannot literally describe what a photon experiences. But the mathematics tells us something deeply suggestive. As an object approaches the speed of light, the amount of proper time along its path shrinks toward zero. That means the journey of light is unlike any journey we can imagine. A photon emitted moments after the Big Bang, and one absorbed billions of years later, has crossed an immense cosmic history from our perspective. Yet the interval measured along light's own path tends toward zero. The universe we inhabit is measured in seconds, years, and billions of years. Light obeys a very different geometry. And once Leonard Susskind begins following that idea to its ultimate consequences, it doesn't merely change how we think about light. It changes how we think about reality itself. If light challenges our intuition about time, it completely shatters our intuition about space. Picture yourself standing on a quiet beach at sunset. You shine a laser toward the horizon. The beam races away at nearly 300,000 kilometers every second, covering the distance from New York to Los Angeles more than 70 times in a single heartbeat. From your perspective, the light is crossing an enormous stretch of space. Now imagine climbing aboard an impossibly fast spacecraft and accelerating until you're traveling at 9,999% of the speed of light. Outside the window, the stars no longer resemble the familiar night sky. According to Einstein's equations, the universe ahead begins to compress. Distances that once seemed unimaginably vast begin to shrink. This effect is called length contraction. And unlike an optical illusion, it is a genuine prediction of special relativity. Objects measured along the direction of motion become shorter for observers moving at extremely high speeds relative to them. Leonard Susskind often reminds his students that relativity isn't simply about moving clocks. Space itself is part of the story. Time cannot change without space changing as well, because together they form the fabric of space-time. Think of space-time as a giant map rather than separate roads and calendars. Every event has both a location and a moment. Change the geometry of one, and the other must respond. This is one of Einstein's deepest insights, and it remains one of the most experimentally verified ideas in all of science. Imagine two cities connected by a straight highway. To someone walking, the trip might take several days. To someone driving, it takes hours. To someone flying, it takes less than an hour. Now imagine a traveler whose speed becomes so extraordinary that the highway itself begins shrinking beneath them. That's closer to what relativity predicts. The traveler isn't simply moving faster across the same distance. The distance itself becomes different. As speeds approach the speed of light, the universe rearranges its measurements to preserve one remarkable rule. Everyone, regardless of their motion, still measures light traveling at exactly the same speed. This is why Susskind emphasizes that relativity is not merely about objects moving through space. It's about space and time adjusting together. Once you accept that, another mystery immediately appears. If no object with mass can ever reach the speed of light, why not? Why can't we simply build a more powerful rocket, a bigger engine, a stronger fuel? Surely enough energy could eventually push a spacecraft all the way there. Surprisingly, physics says no. Every time you increase an object's speed, adding more energy becomes less effective at increasing its velocity. Instead, more and more of that energy contributes to its relativistic energy and momentum. The closer you get to light's speed, harder each additional acceleration becomes. Imagine pushing a massive boulder uphill. At first it moves, then the hill becomes steeper. With every step, the slope increases. Eventually, no matter how hard you push, reaching the summit would require an impossible amount of effort. That's what approaching light speed is like. To accelerate an object with mass all the way to the speed of light would require infinite energy. Infinite. Not an enormous amount. Not technology we haven't invented yet. An amount that nature simply does not allow. The universe has built a speed limit directly into its foundations. Light doesn't obey that limit because it was never accelerating toward it. Light has always traveled at that speed. Photons, the particles associated with electromagnetic radiation, are massless. Because they have no rest mass, they don't need to be accelerated from rest to light speed. In vacuum, they simply propagate at the universal speed determined by the laws of electromagnetism and relativity. That simple fact separates light from almost everything else in existence. But what exactly is a photon? For centuries, scientists argued endlessly about this question. Was light a wave or was it a particle? Newton believed particles made the most sense. Then experiments demonstrated interference patterns that could only be explained by waves. The debate appeared settled, until another experiment overturned everything once again. In 1905, the same miraculous year Einstein introduced special relativity, he also explained the photoelectric effect. When light strikes certain metals, electrons are ejected. Oddly, making the light brighter didn't always produce the expected result. Instead, the color, or more precisely, the frequency, of the light determined whether electrons escaped. Einstein proposed something astonishing. Light sometimes behaves as though it arrives in tiny packets of energy. Each packet carries a precise amount of energy determined by its frequency. Those packets became known as photons. At first, many physicists resisted the idea. How could light be both a wave and a particle? It sounded contradictory. Yet experiment after experiment forced scientists toward an uncomfortable truth. Light behaves differently depending on how you investigate it. In some situations, it spreads like a wave across space. In others, it exchanges energy as discrete quanta. This isn't because light changes its mind. It's because nature at the quantum level doesn't fit neatly into the categories our everyday experience has taught us. Leonard Susskind has spent decades explaining this strange reality through quantum mechanics, a theory that is simultaneously one of the most successful and one of the most counterintuitive frameworks ever developed. Quantum mechanics doesn't tell us that common sense is useless. It tells us that common sense evolved for survival on the African savanna, not for understanding photons, atoms, and black holes. One of the most famous demonstrations of light's bizarre behavior is the double slit experiment. Imagine a barrier with two narrow openings. Behind it sits a screen capable of recording every arriving photon. If light consisted only of tiny particles, you would expect two bright bands directly behind the slits. Instead, when many photons arrive, an interference pattern appears, alternating bright and dark stripes characteristic of waves. Even stranger, if photons are sent one at a time, each individual photon lands as a single localized event. Yet after enough have arrived, the same interference pattern gradually emerges. It's as though each photon contributes to a larger statistical pattern described by quantum mechanics. This result has been confirmed repeatedly, although its interpretation remains one of the deepest questions in physics. Different interpretations explain the mathematics in different ways, but they all agree on the experimental predictions. Susskind often encourages students not to confuse the mathematical success of quantum theory with certainty about its philosophical meaning. Physics predicts outcomes extraordinarily well. Why those equations describe reality so perfectly is a separate question, and perhaps an even deeper one. The mystery grows even stranger when light encounters gravity. For centuries, gravity seemed simple. Newton imagined an invisible force pulling every object toward every other object. Apples fell, planets orbited, everything behaved predictably. Einstein replaced that picture with something far more elegant. Mass and energy don't pull on space, they reshape it. Imagine placing a heavy bowling ball on a stretched rubber sheet. The surface bends. Roll a marble nearby, and it follows the curved surface. This analogy isn't perfect. Real space-time curves in 4 dimensions, not 2, but it captures the essential idea. Planets orbit the sun not because an invisible force reaches across empty space like a cosmic rope, but because they follow the straightest possible paths through curved space-time. And light does exactly the same thing. That seems impossible at first. How can gravity affect something with no rest mass? The answer is subtle. Gravity isn't pulling on the photon in the Newtonian sense. The photon is following the geometry of space-time itself. When space-time bends, the path of light bends with it. This prediction seemed outrageous when Einstein first proposed it. Then came the solar eclipse of 1919. Astronomers photographed stars positioned close to the eclipsed sun. Their apparent positions had shifted. The starlight had curved while passing through the sun's gravitational field. Einstein's theory had survived one of its first great tests. Since then, gravitational lensing has become one of astronomy's most powerful tools. Entire galaxies act like enormous cosmic lenses. Clusters of galaxies magnify even more distant objects hidden behind them. Light, which once seemed to travel in perfectly straight lines, reveals that space itself is anything but straight. And if gravity can bend light, what happens when gravity becomes so overwhelming that even light cannot escape? That question would lead physicists, including Leonard Susskind, into one of the greatest scientific mysteries ever discovered, where relativity and quantum mechanics collide, and where our understanding of reality itself begins to unravel. The answer lies in one of the most extraordinary predictions ever made by science: the black hole. For a long time, black holes sounded like mathematical curiosities rather than real objects. Even Einstein himself was skeptical that nature would ever allow something so extreme to exist. Yet the equations of general relativity refused to let them disappear. If enough matter collapsed under its own gravity, space-time would become so severely curved that a boundary would form, a point of no return known as the event horizon. From outside that boundary, something astonishing happens. Imagine watching an astronaut fall toward a black hole while you remain safely far away. As the astronaut approaches the event horizon, your view becomes increasingly strange. Their clock appears to slow. Their movements become sluggish. The light carrying their image loses energy, stretching into longer and redder wavelengths. To you, it looks as though they are freezing in time, fading away without ever quite crossing the horizon. But that isn't what the astronaut experiences. Their own clock continues ticking normally. They don't feel time stopping. They don't notice the universe freezing around them. As far as they are concerned, they continue falling toward the horizon in a perfectly finite amount of time. How can both stories be true? This is where Leonard Susskind introduced one of the most profound ideas in modern theoretical physics. He argued that both descriptions can be valid because they belong to different observers, and no observer can directly compare those contradictory experiences. This concept became known as black hole complementarity. It doesn't claim that reality is inconsistent. Instead, it suggests that the universe can present different, equally valid descriptions depending on where the observer is located, provided those descriptions can never be experimentally combined into a contradiction. At first glance, this sounds almost philosophical, yet it emerged from an intensely practical problem. According to quantum mechanics, information cannot simply vanish. If you know the exact quantum state of a system, the laws of physics allow that information to evolve but not to be erased from existence. Black holes seem to violate that principle. Anything falling inside appeared to disappear forever. Then, in the 1970s, Stephen Hawking discovered something completely unexpected. Black holes are not entirely black. By combining quantum field theory with curved spacetime, Hawking showed that black holes should emit a faint thermal radiation, now called Hawking radiation. Over unimaginably long periods of time, that radiation carries energy away. The black hole slowly loses mass and can eventually evaporate. This remarkable prediction is widely accepted by physicists, although Hawking radiation has not yet been observed directly because it is far too weak for astrophysical black holes. Its implications, however, were enormous. If a black hole eventually disappears, where does the information go? Does it vanish? Does quantum mechanics fail? Or is our understanding of black holes incomplete? This became one of the greatest unsolved puzzles in theoretical physics. Leonard Susskind refused to believe that quantum mechanics was wrong. Instead, he spent decades developing ideas that would preserve one of its most fundamental principles: information is never destroyed. His work helped transform the debate and ultimately influenced what many physicists now consider the most likely resolution of the paradox. One of the boldest ideas to emerge from this effort is the holographic principle. The name sounds like science fiction, but the concept is rooted in rigorous mathematics. Imagine holding a credit card hologram. The image appears three-dimensional, yet the information needed to create that illusion is stored on a two-dimensional surface. Now imagine something even more astonishing. What if the entire three-dimensional universe worked in a somewhat analogous way? What if all the information contained within a region of space could be fully described by information encoded on its boundary? This is not an established fact about our universe in every context. It is a powerful theoretical idea supported by compelling evidence in certain models of quantum gravity, particularly through developments in string theory. Susskind became one of its strongest advocates. If true, it would mean that our familiar three-dimensional reality could emerge from deeper principles written on a lower dimensional surface, much as a hologram emerges from a flat sheet. It's an idea that reshapes our intuition as dramatically as Einstein's relativity once did, and light is central to the story. Every observation you've ever made of the universe has arrived through light. Every galaxy, every nebula, every planet orbiting a distant star. Even this moment, as your eyes scan these words, exists because photons are constantly carrying information toward you. Light is not merely illumination. It is the messenger that allows the universe to reveal itself. Yet even that messenger has limits. Because light travels at a finite speed, looking farther into space also means looking farther into the past. The moon appears as it was about 3 seconds ago. The sun as it was roughly 8 minutes ago. The Andromeda galaxy as it was over 2 million years ago. Some of the galaxies captured by powerful space telescopes appear as they existed more than 13 billion years ago, when the universe itself was still young. Astronomy is unlike any other science. Its observations are historical records carried across cosmic time. Every telescope is, in a very real sense, a time machine. This realization changes how we think about the night sky. The stars are not showing us what exists now. They are showing us what once existed. Some may already have changed dramatically. Some may no longer exist at all. The universe we see is always slightly older than the universe that is. And perhaps that is the greatest lesson hidden within light. We began with a simple question: does light move the way we think? The answer turned out to be far stranger than anyone expected. Light does not simply race through an empty stage called space. Its constant speed forces space and time themselves to adjust. It reveals that clocks are not universal, that distances are not absolute, that gravity is geometry, that black holes challenge our deepest assumptions about information, and that reality may possess layers more subtle than anything our everyday experience prepares us for. Leonard Susskind has often argued that the history of physics is a history of abandoning comfortable intuitions in favor of deeper truths. Each generation discovers that reality is not obligated to resemble common sense. Again and again, nature surprises us, not because it is irrational, but because it is richer than the world our senses evolved to perceive. Perhaps the most remarkable fact is not that the universe is strange. It is that the human mind, built from atoms forged inside ancient stars, can uncover these hidden patterns at all. We can write equations describing the birth of galaxies. We can predict the bending of light around invisible black holes. We can measure tiny quantum effects with astonishing precision. And yet, despite all we've learned, we still don't know how quantum mechanics and gravity fit together into one complete picture. We still don't know whether space-time itself is fundamental or emergent. We still don't know whether the holographic principle describes our universe in its deepest form. So the next time a beam of sunlight falls across your hand, remember that you are not simply seeing light. You are witnessing the behavior of something that has forced humanity to redefine space, time, gravity, and reality itself. And if a single photon can lead us to question everything we thought we knew about the universe, what other truths are hiding in plain sight, waiting for us to realize that we've been looking at them the wrong way all along?